let's see. So here we go with today's section on real zeros of polynomials. So the real zeros of polynomial section here. So the first thing is the rational zeros of polynomials and the rational zeros theorem. So here it is. If the polynomial p of x is equal to a sub n x to the n plus a sub n minus 1 x to the n minus 1 all the way to a sub 1 x plus a sub 0 has integer coefficients where this leading coefficient and the constant term are not equal to 0, then every rational zero of p, this polynomial here, is of the form p over q, where p and q are integers, and p is a factor of the constant coefficient a0. So the a0 will be where we get the factors for the p, and the an is where we're going to get the factors for the q. So these will be where we get the factors for the q. All right, now I actually think that this is a little bit confusing in a way, because usually, like, if we're reading from left to right, p would be first and then q, but we have to remember these are going to be the p's and these are going to be the q's. So then we're going to use these steps to try to find the rational zeros of a polynomial. So we're going to list all the possible zeros using the rational roots or the rational zeros theorem, because I sometimes say rational roots theorem because zeros are roots, so that's another word for that. And then we're going to divide, but we're going to use synthetic division. You don't have to do that, but that would be the quickest way to do this. To evaluate the polynomial, each of the candidates for the rational zeros that you found in step 1, and then when the remainder is 0, note the quotient you have obtained, and then repeat until you aren't able to do so anymore, meaning that you get something that you can factor easy, or just use the quadratic formula to go ahead and find the rest of the zeros. Now, remember that these are only going to be for the rational zeros, so if you have a zero or a root that's irrational, then this theorem will not find those zeros. So, example 1 here. Use the rational zero theorem to find the rational zeros of f of x is 2x to the fourth plus 5x to the third plus x squared plus 10x minus 6, and then use the results to factor f of x, and then use the graph to assist in determining likely candidates for the rational roots. All right, so I know here that the roots look to be at around -3 here, and somewhere maybe around a half. All right, but we can verify that in a moment. So remember that the q's are the factors of this coefficient of the leading term. So we know that this is going to be a sub 0, a sub 1, a sub 2, a sub 3, a sub 4. So it's a4 in this case because this is a fourth power term here. So we have a4 is equal to 2, and then we have the q's. All right, so the q's are the factors of 2. So actually that actually looks a little bit strange the way that I wrote the s there, but then I know that there's lots of factors of 2 because 1 times 2 is 2, and -1 times -2 is also 2. So we have plus or minus 1 and plus or minus 2 are all factors of 2. And then, let's see here, we have the a0 is -6, so the p will be the factors of -6. So that would be similarly plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. All right, so these are all the numbers that go evenly into the -6 here. So now we need to write out the p's over the q's here. So the p over the q's. So we're going to take all of the p's here. So plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, and then divide these by all of the q's. So I'll start by dividing them all by the 1. So plus or minus 1, plus or minus 1, plus or minus 1, plus or minus 1. Then I'm going to, so I already did the 1. So then I'm going to take all of the p's, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, and then divide them all by the 2. So plus or minus 2, plus or minus 2, plus or minus 2, plus or minus 2. And then what I'll do is I will simplify these so that I can make sure there's not any duplicates to make sure that it's less work for me. So 1 over 1 is 1, so plus or minus 1. 2 over 1 is 2, so plus or minus 2. 3 over 1 is 3, plus or minus 3. 6 over 1 is 6, so plus or minus 6. Then 1 over 2 is a half, so plus or minus a half. But then 2 over 2 is 1, so I already have that on the list, so I don't need to repeat that. Then I have 3 over 2, so plus or minus 3 over 2. And then I have the 6 over 2, which is 3, but 3 is already on my list, so I don't need to repeat that. All right, so now, so let me find the next page here. All right, so now what I'm actually going to do is I'm going to actually write the f of x on the top of the next page, just so that I know that I don't have to keep on looking for this. And then what I really need to do is make a guess at what these zeros are. So the first one I see might be -3, and -3 is on my list. And the next one I see might be a half, and a half is on my list. So I already know those are probably it. All right, so I'm just going to confirm that through using the synthetic division. So let's start with the -3 here. So to use synthetic division, I have the -3. C is -3. That will be my possible rational root here. And then I have all the coefficients of the f of x, or the p that I've been calling it. All right, so this p for polynomial, but this f of x is clearly a polynomial, so it's just a different letter here other than p. Then I'll write the coefficients down: 2, 5, 1, 10, -6. Then I'll bring down the 2. All right, so -3 times 2 is -6. And then add 5 minus 6 is -1. Multiply -3 times -1 is actually, what is that? That will be 3. And then 1 plus 3 is 4. -3 times 4 is -12. 10 minus 12 is -2. Then -3 times -2 is 6, and -6 plus 6 is 0. So this is the remainder. So what that means then is that the c equals -3 is a 0 of the p, or the f of x here. And then that also means that x minus a -3, or x plus 3, is a factor of the p. All right, so now what I need to do, so again, when I divide it, I need it to make sure that the remainder was 0, because that means that this part here will be a factor of p. And then I repeat this same division step for the quotient. So the quotient would be here the 2x to the third minus x squared plus 4x minus 2. So I'm going to repeat this step for the quotient, and remember that I said the other 0 is probably at a half. All right, so I'm going to repeat this with a half as the c here. So I have my coefficients for the quotient, 2, -1, 4, and a -2 here. Then I'll bring down the 2. A half times 2 is 1. Then -1 plus 1 is 0. Then a half times 0 is 0. So 4 plus 0 is 4. And then a half times 4 is 2, and -2 plus 2 is 0. So there is another remainder of 0. So that means that c equals a half is a 0 of p, and x minus a half is a factor of p. All right, so now let's see. What do we have here? So the new quotient here is actually going to be 2x squared plus 0x plus 4. So this is a quadratic. So remember that I said in step 3 here, we could stop when we reach a quadratic or something that factors easily. So this is quadratic, so we can stop. And this is a factor of p also. So that means p equals f of x is equal to 2x to the fourth plus 5x to the third plus x squared plus 10x minus 6 is equal to this 2x squared plus 4, and then this x minus a half, and then the x plus 3 that we had. And then you can actually see here that you can factor out a 2 from this quadratic right here. So we have 2 times x squared plus 2 times x minus a half times x plus 3. And now, normally when you factor, you wouldn't actually see a fraction like this. So here's what actually happens. I'm going to take this 2 right here. All right, so this 2, and I'm going to go ahead and distribute it into this factor here. So I have x squared plus 2 times 2x minus 1 times x plus 3. So this is what I end up with as the result of factoring f of x. Now, notice that I could look at 2x squared plus 4, by the way, and see that I could subtract the 4 and divide by 2, and then take the square root. So x would be plus or minus the square root of 2i, because this is imaginary with the negative number under the square root there, but we weren't factoring with the imaginary numbers quite yet. That will actually be the next section, because those imaginary roots are not roots that you can see on the two-dimensional graph. And actually, I saw a very interesting article about how you could visualize those imaginary roots. All right, so that is the first example there. So again, if I'm going too quickly or if you have any questions, just throw them in the chat there, but right now I was actually going to look for the next page. And the worst part here is that my pen keeps on falling on the floor because I have a pen with a cap that doesn't stay on very well, so I'm actually going to switch pens here. So example 2. This one is a little bit different here. So sorry about that. My lights actually turned on because they're on a timer that only lasts 1 hour for some reason, and I can't change it. So change and okay. So what happens if you don't have a remainder of 0? So let's actually, you know what? I'll show you an example of that on this one here, because in the last example, I think you could see that we kind of used the graph to help us figure out that -3 was on the list and would be close, and then the next one was between 0 and 1, and the only number on here that was between 0 and 1 was a half. All right, so if I pick a number that's not one of these, then I would get a remainder that's not 0, and then I would just know that that wasn't actually one of the roots. But I'll do an example of that in this next problem here. So use an equivalent form in the rational zero theorem to find the rational zeros of this function. F of x is equal to 2/3 x to the 4th minus 5/2 x squared plus 5/6 x plus 1, and use the rational zeros to factor the function expression. So I'm actually going to write this as just y is equal to 2/3 x to the 4th minus 5/2 x squared plus 5/6 x plus 1. Then I'm going to, when I say use an equivalent form here, that means I can actually just multiply by well, one way to do this is actually just to multiply by 6 to clear the fraction. So 6, 6, 6, 6, 6. So I have 6y is, all right, so 6 times 2 over 3 is 12 over 3. So I have 4x to the 4th. And then 6 times 5 over 2 is 30 over 2. So I have minus 15x squared. Then 6 times 5 over 6 is just 30 over 6, or 5. So I have 5x, and 6 times 1 is 6. Then I can divide by 6. So I have y is 1/6 times all of this here. All right, so now what I can do is actually just look at this expression without the 1/6 involved. All right, so the A4 will be 4, and the A0 will be 6, and so the 4 is what I'm going to look at for the Q. So the Q will be the factors of 4, so plus or minus 1, plus or minus 2, plus or minus 4, and the P will be the factors of 6. So that will be, I'm going to focus that a little bit better, and I actually do not like this pen, so I'm going to switch to something darker. Hopefully that will make a little bit better viewing. So this will be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. And then what I'll do here is I'll go ahead and I'll graph the where is it? The 4x to the 4th minus 15x squared plus 5x plus 6. So if I do that, here is my sketch of it. All right, so now I know that this is going to be, I actually don't know why this actually looks like this. This is really, my calculator has been doing this all week, where there's a bit of a weird a line under it, but well, anyway, I'll sketch in a second, because I'm going to try to figure out how I get the weird line off of there. So P over Q again. So then I need the factors of P divided by the factors of Q. So I'll take all these plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, and divide them all by the plus or minus 1. And then I'll take all of the P's and divide them by the plus or minus 2. So plus or minus 2, plus or minus 2, plus or minus 2. And then all of the P's, and divide them all by the plus or minus 4. And then I'll do all the divisions and just make sure that there are no repeats. All right, so I actually am going to figure this one thing out real quickly with my calculator. So I actually don't know why, like I said, my calculator is drawing that weird line so that I can't actually see the x-axis, but so the graph sort of looks something like oof. All right, so oops. Yeah, I'm still, for some reason, seeing those weird lines on my calculator. So I'm going to try to type it into the computer real quickly to see if I can get a better graph. Maybe not, but anyway, here it is. So there's a 0 here, a 0 here, and a 0 here, and a 0 here, and the graph looks like it goes down and then back up and then down and then back up. All right, so something like this. All right, so now let's simplify all these possible roots here. So 1 over 1 is 1, 2 over 1 is 2, 3 over 1 is 3, 6 over 1 is 6, 1 over 2 is a half, 2 over 2 is 1, but that was already on my list, so I don't need that again. And then 3 over 2 is not a repeat. And then 6 over 2 was 3, but that was already on my list over here. Then 1 over 4, and then 2 over 4 was a half, but that was already on my list. Then 3 over 4, and then 6 over 4 is 3 over 2, but that was already on my list. So I already got some of these taken off of the list by just taking out the repeats here. Now, I see that this is sort of close to -2, but let's say, for example, I thought that it was actually closer to -3. You realize, like, I actually knew that it wasn't going to be 0, but I saw 4x to the thirds, but I wasn't even looking. But technically, you should have put the 0x to the third in there also, and that would have given you a different remainder. Not something that still wasn't 0, but just so that you're aware that that I realize now that I looked at the problem wrong here. So just as a heads up, that's a mistake that is that common to make. And this particular one I made because I looked at the problem wrong and thought it said 4x to the third. So I just want to write that for you so that there isn't any confusion with you later on. And actually, I'm glad that I noticed that because I actually realized that when I looked at it again that this was going to be the wrong remainder, but that's okay. It still wasn't 0, so 174. So it is, was it 180 and not 280 something. But in either case, so 4x to the fourth, and then we have 0x to the third, and then we have negative 15x squared plus 5x plus 6. So bring down the 4. Negative 2 times 4 is negative 8. Then I'll add 0 plus negative 8, negative 8. Then negative 2 times negative 8 is 16. And then negative 15 plus 16 is 1. And then negative 2 times 1 is negative 2. 5 minus 2 is 3, and then negative 2 times 3 is negative 6, and then 6 minus 6 is 0. So there is my remainder of 0. So a remainder of 0 means that c equals negative 2 is a 0 of p, and then x minus the negative 2, or x plus 2, is a factor of p. And then I just do this again, just like the last problem. So, oops, I thought I had a blank piece of paper, but that was actually my tax return. So let me find a blank piece of paper here. So now I'm going to look at what the q of x is, and because I looked at the wrong function for the last one here, I'm going to make sure that I write it down at the top of the page this time so I don't look at the wrong exponent. So what do I have? I actually have 4x to the third minus 8x squared plus x plus 3. So now if I look at what the other zeros look like they are here, if I look at the graph, another one looks like it might be at negative a half. So I'm going to try a negative a half here. So negative a half, and then the coefficients of this remainder, 4, negative 8, 1, and 3. Then bring down the 4. Negative a half times 4 is negative 2. Negative 8 plus negative 2 is negative 10. Then a negative a half times negative 10 is 5, and 1 plus 5 is 6, and negative a half times 6 is negative 3. 3 minus 3 is 0. So this is a remainder of 0. So that means c equals negative a half is a 0 of p, and x minus a negative a half is a factor of p, so that's x plus a half. And then my new q of x then is going to be the, what is it, 4x squared minus 10x, and then plus 6. And you can keep on going at this point if you would like, or you, because it's a quadratic, I can just factor it from this point. So I can factor out a 2 to get 2 times 2x squared minus 5x plus 3. And then I can factor this part into 2x and x. So that should be, what is it? Well, that should be a plus 3 and a minus 1, I think. No, minus. Okay, there we go. I was staring into space again, and I see that I have 2x squared minus 2x minus 3x plus 3 gives me 2x squared minus 5x plus 3. So these are the other factors of p. So therefore, the f of x equals 2/3 x to the fourth minus 5 halves x squared plus 5 6x plus 1 will be, we had the 1/6 that we had out in front here that you don't want to forget about. Then you had a factor of x plus 2, and then you had a factor of the x plus a half, and then you had the 2, and then the 2x minus 3, and then the x minus 1, and then again, it looks a little bit odd to have the fractions in here like this, so I'll distribute the 2 in here. So I'll have 1/6 x plus 2, 2x plus 1, 2x minus 3, and then x minus 1. So there you go. That is the f of x. So not only is this theorem of the rational roots important to find the zeros of the graph, but it also is helpful in factoring the polynomial if you don't know what some of the factors are. All right, so there's that. Now let's go ahead and look at the next one. So if you have any other questions, just put those in the chat too. But I feel like this gets repetitive and it gets a little bit boring at times. And what you just need to remember is just look at the graph and then use the graph to help you figure out what these good guesses are, so that you don't spend a lot of time looking at roots that aren't ones that are actually the roots. So you don't want to look at all the possible roots if you have a graph to sort of give you a good guess at what they are. So here is Descartes' rule of signs. So let p be a polynomial with real coefficients. And I say real because in the next section we might have some that aren't real. And the number of positive real zeros of p of x is either equal to the number of variations in sign in p of x or less than that by an even whole number. And then what I actually mean then is that it's equal to the number of variations in the sign of p of x or less than that by an even whole number. So let's say that the number of variations was say 5. Then less than that by an even whole number would be minus 2 to get 3, minus 2 to get 1. All right, so it could be 1, 3, 5, or it could be, if it's an even number to start with, it could be 6, 4, 2, 0. All right, so you start at the number that you have of variations of signs and then count down by 2s until you either get to a 1 if you start at an odd number, or to 0 if you start it with an even number. All right, and then the number of negative real zeros of p of x is either equal to the number of variations in sign of p of the opposite of x, or is less than that by an even whole number. All right, so again, just remember that that follows the same scenario, that if you start at, say, at 9, then you would have 9, 7, 5, 3, 1. And if you start at, say, 10, 10, 8, 6, 4, 2, 0. All right, so use Descartes' rule of signs to determine the possible number of positive real zeros, negative real zeros, and imaginary zeros of each function. So I know that this is actually to the third power. So the third power means, or degree 3, means that there must be 3 solutions. All right, so degree equal to 3, that means that there must be be three zeros total. All right, so now what do I mean by the variation in sign? So if I look at this, here is a positive 2 coefficient, a -5, a -8, and a positive 11. So if I go from a positive, then to a negative coefficient, then a negative, and then a positive, a variation is a change from a positive to a negative or a negative to a positive. So a positive to a negative is one change, and so that's one change. But then it's negative, negative, that did not change, and the negative to a positive, that's one change. So I know that f of x has two variations in sign. So that means that the number of positive real zeros is 2 or 0. All right, so remember that I have to, if I start at 2, I have to count down by 2 until I get to 0. So now to find the possible number of negative real zeros, so I need to find p of negative x. So f of negative x, so I'm going to use f of negative x to find the number of possible negative real zeros. All right, so that will be 2 times the opposite of x to a third minus 5 times the opposite of x squared minus 8 times the opposite of x plus 11. So that will be negative 2x to a third minus 5x squared plus 8x plus 11. And then, let's see, so now I have a negative 2 and a negative 5 and a positive 8 and a positive 11 as my coefficient. So negative to a negative is not a change in sign, but negative to a positive is. So there's one change, and then a positive to a positive is not a change. So f of negative x has one variation in sign. So the number of negative real zeros is 1. And then remember, if I start at 1, then I'm done. If I start at 3, it could be 3 or 1. If I start at 5, it could be 5, 3, or 1. So then I'm going to make a chart of the possibilities. So if I have number of positive real zeros and number of negative real zeros. Okay, so yeah, is this, I see your comment now, so is that supposed to be positive 5? No, because this is actually negative 5 times negative x times negative x, so then there's 3 negatives there, so it's still negative. So that is why that one's actually negative. So that's why I put the negative x in the parentheses to make sure that I wouldn't make any error in that. So hopefully that's the 5 that you were talking about. And then I have actually a column for the imaginary zeros, and then for the total. Okay, good. So I'm glad that I saw that 5 there. Yeah. So now remember the possibilities for the number of positive real zeros were 2 or 0. So 2 or 0. So remember that the total had to be 3. All right. So if there were one possible negative real zero. All right, so here we go. So 2 plus 1 is 3, so that means that there would be 0 imaginary zeros in this case. And remember, the total is 3. So if there were 0 real zeros and 1, so 0 positive real zeros and 1 negative real zero, then that must mean that there's 2 imaginary zeros. All right, so in either case, the total needs to be 3. Now, if I look at the graph here, so let me just show you the graph of this. So if I actually had f of x was 2x to the third minus 5x squared minus 8x plus 11, and I graphed this, then 2x to the third minus 5x squared minus 8x plus 11, and I see the graph here, and you can see right here that there was 1 negative 0 and that there were 2 positive zeros. So that means that this is what actually happened. But even though this is a possibility that there were 0 positive real zeros and 1 negative real zero and 2 imaginary zeros, that's not what actually happened here. What happened was that there was 1 negative 0 and 2 positive zeros, and that made 3 total. So the reason why this would be useful is, let's say that we're doing the last example, right? And then I knew that there were supposed to be, let's say, 2 negative zeros, then that would mean that after I found the 2 negative ones, I could actually not test any more of the negative numbers on the list. All right, so that's why people came up with this theorem, this Descartes Rule of Signs, was to help them sort of narrow down what numbers they needed to do the long division for. So there's that. So let's try another one here. So we have 4x to the 7th plus 3x to the 6th plus x to the 5th plus 2x to the 4th minus x to the 3rd plus 9x squared plus x plus 1. So now I'll look at the coefficients again. So we start with the 4, so that's positive, then the 3 positive, then the 1 positive, the 2 positive, negative 1 negative, positive 9, positive 1, positive 1. So I see one change from positive to negative, a change from negative to positive, and then that looks like that's all of the possible changes here. So f of x could have 2 or 0 positive real zeros. All right, so now I want to look at the f of negative x now, or f of the opposite of x, at 4 opposite of x to the 7th plus 3 opposite of x to the 6th plus opposite of x to the 5th plus 2 opposite of x to the 4th minus opposite of x to the 3rd plus 9 opposite of x squared plus opposite of x plus 1. And then if I have 7 negatives here, that's actually negative. So negative 4x to the 7th. 6 negatives, that's an even number of negatives, so that's positive. So plus 3x to the 6th. 5 negatives, negative, so minus x to the 5th. 4 negatives, positive, so plus 2x to the 4th. 3 negatives is negative, but then it's minus a negative x to the 3rd, so that would be positive x to the 3rd. And then you have 2 negatives, so that's positive, so plus 9x squared minus x plus 1. All right, so now let's look at the changes in sign. So negative, positive, negative, positive, 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 negative, positive. So here's one change, negative to positive, positive to negative, negative to positive positive is not a change, positive to positive not a change, positive to negative a change, and negative to positive a change. So there were 1, 2, 3, 4, 5 changes. So f of x could have, so 5, and then I remember back that it has to be subtract 2 until I get down to 1, since I start at an odd number like a 5. So 5, 3, or 1, negative real zeros. All right, so then I also noticed that f of x was of degree 7. So f of x is degree equal to 7. So there must be 7 total zeros. So then I can make a chart just like before of the possibilities. So here's the possibilities of the number of positive real zeros and the number of negative real zeros and the imaginary zeros, and then the total. So I know that for the positives we had 2 or 0, and then for the negatives we could have 5. So we could have 2, 5 or 0, 5. Or we could have had 3, so 2, 0, and then 2, 3, 0, 3. And then we could have had 1, so negative real 0, so 2, 0, 1, 1. All right, so we write out all the possibilities, 2, 5, 0, 5, 2, 3, 0, 3, 2, 1, 0, 1. And then the total was 7. So for all of these, we know the total was 7. And then here we go. So we see that if there's 2 plus 5, that means that there's 0 imaginary. 0 plus 5, that means 2 imaginary. 2 plus 3 is 5, so that means I need to do 2 imaginary. 0 plus 3 is 3, so 3 plus 4 is 7, so 4 imaginary. 2 plus 1 is 3, so 4 imaginary. And then 0 plus 1 is 1, so that would be 6 imaginary. And another thing to notice is that all of the imaginary zeros numbers here are even, and that's because imaginary zeros will always come in pairs. So these all should always be 0, 2, 4, 6, because all the imaginary zeros or imaginary roots will come in pairs or groups of 2 like that. All right, so now for the upper and lower bounds theorem here. So let P be a polynomial with real coefficients, and you'll divide P of x by x minus b using synthetic division, and if the row that contains a quotient and remainder has no negative entry, then b is an upper bound for the real zeros of P. And so what that actually means is that you're going to use this theorem to sort of say that there is, say, like a upper bound of what these zeros could be, and then like let's say it was like 3, then if 3 is the upper bound of what the zeros could be, then I wouldn't actually need to check 6. All right, so that's why we would use a theorem like this to eliminate even more numbers off of this long list of numbers that we would possibly need to check to be the rational zeros. So there is a reason for all these theorems, and it's just to help you make that laundry list of numbers that we saw from that first theorem a little bit shorter. So then similarly, if you divide p of x by x minus a, with a is less than 0 using synthetic division, if the row that contains the quotient remainder has entries that are alternately non-positive and non-negative, then a is a lower bound for the real zeros of p. So use the upper and lower bounds property above to verify that all the real, real zeros of the f of x is x to the fifth minus 4x to the fourth plus 2x to the third minus 5x plus 2 lie between -6 and 6. So that means that -6 and 6 are respectively lower and upper bounds for the real zeros. All right, so let's start with the -6 here. So f of x, we have x to the fifth plus 4x to the fourth plus 2x to the third, and then don't forget that 0 for the x squared term minus 5x plus 2. So 1, -4, 2, 0, -5, 2. And notice I rewrote it this time so that I wouldn't look at the wrong exponent and forget the 0 again. So bring down the 1. -6 times 1 is -6. -4 plus -6 is -10. Then -6 times -10 is 60. So 2 plus 60 is 62. And then -6 times 62 is -372. So 0 plus -372 is -372. Then -6 times the -372 is 2,232. So -5 plus 2,232 is 2,227. Then -6 times the 2,227 is -13,362. So then if I add these together, 2 minus 13,362, that's -13,360. All right, so then let's see. Well, all right, so now just remember that if you're dividing by a number where this is less than 0, then you need to look to see if these are alternately non-positive and non-negative. So we have a positive, a negative, a positive, a negative, a positive, and a negative in the bottom row here. So these did alternate positive, negative, positive, negative, positive, negative. So these are alternating in sign. So what does that mean? It means that -6 is a lower bound for the real zeros of f of x. All right, so hopefully that all makes a little bit of sense here. So now let's see, we have the 6 here. So 6, and so we'll do the same thing for the 6 to see if 6 is the upper bound. So 6, and then 1, -4, 2, 0, -5, 2. We'll bring down the 1. So 6 times 1, 6. -4 plus 6 is 2. 6 times 2, 12. 2 plus 12, 14. 6 times 14 is 84. 0 plus 84, 84. 6 times 84 is 504. So -5 plus 504 is 499. And then 6 times 499 is 2,994. So 2 plus 2,994 is 2,996. So then for a positive number, you want no negative entry. So all positive numbers here. So +1, +2, +14, 84, positive 499, positive 2,296. So all positive or non-negative, meaning that it could be 0, by the way, but non-negative. So then what does that mean? Well, that means, therefore, 6 is an upper bound for the real zeros of f of x. All right, so hopefully that all makes sense. So just a note about this, and I'll show it on the calculator again if I can find this. So here we go on, and if I show this on the calculator, the graph here, then I have x to the 5th minus 4x to the 4th plus 2x to the 3rd minus 5x plus 2. And then if I graph this, I can see that there's a 0 right here, a 0 right here, a 0 right here. But none of the zeros are actually below -6, and none of the zeros are above 6. So that's what I mean by the lower and upper bounds, is that all of the zeros happen to be between -6 and 6. And I could close that in and say between -5 and 5, or wherever I need to close it into to try to eliminate some of the possibilities for where the real zeros might be. All right, so before we move on, do you have any questions, Luca? And then I don't actually know if where the next page is, but I don't think that this section here is actually a lot of work. It's just that some of the items here are, in my opinion, a little bit tedious, and so there's that as well. So here we go. So